Hello everyone, my name is Rover Jr. and I'm the current President and Chief Engineer of SEDS at NC State. I'm currently a senior studying aerospace engineering along with a minor in physics.
Hello, my name is Preston Scott. I'm a sophomore here at North Carolina State University studying computer science, and I'm the public relations officer here at SEDS.
Hello everyone, my name is Matthew. I'm a sophomore in aerospace engineering here at North Carolina State University, and I'm the mechanical sub-team lead.
Hey, my name is Praneet Lokanani, and I'm a freshman in aerospace engineering here at North Carolina State University as a general member.
Today we'll discuss about what our club is, what we do, things besides the University Rover Challenge, along with go to dev, what we're actually doing in the competition. And to start, the Students for the Exploration and Development of Space at North Carolina State University is a student-led organization focused on the space exploration technologies. For the 2025 University Rover Challenge, otherwise known as URC, our team of undergraduate students have been designing and developing a Martian rover capable of performing mission tasks in a simulated Mars environment.
Now, in our second year of URC participation, our main goal is to manufacture and assemble the first fully functional iteration of the rover. Building on last year's research and design, we have made significant progress in manufacturing key subsystems.
A 30% budget increase from last year has accelerated manufacturing, allowing us to produce higher quality materials and expand testing. Additional financial support has also enhanced prototyping, software development for autonomous navigation, and testing environments.
The chassis has been refined for durability and weight optimization, while the rocker bogie suspension system has been fabricated and tested. The wheel system, featuring 12-inch polyurethane or beach wheels, has been finalized for improved traction and stability. Since August 2024, the robotic arm system has been developing, transitioning from research to manufacturing.
Moving forward, we remain focused on iterative improvements, rigorous testing, and system integration to ensure the rover is competition ready. With a multidisciplinary team and advanced engineering tools, we aim to develop a capable rover and achieve a strong standing in URC.
The suspension system utilizes a modified rocker bogie configuration, incorporating design enhancements to improve terrain adaptability. This design has also been widely adopted by university teams competing in the University Rover Challenge due to its proven reliability and low-risk implementation. This configuration enhances the rover's ability to maintain stability and traction by allowing the wheels on either side to adjust dynamically to obstacles and elevation changes.
We will be using 6 11.8-inch polyurethane balloon tires. These are most useful for the material's ability to resist wear and or abrasion, which, coupled with its cushioning property, makes it optimal for the rover to traverse through rugged terrain.
The frame of our rover consists of a solid chassis and base designed from 606 aluminum, which is integrated with our rocker bogie suspension system. The frame was designed to properly space out our other systems while protecting the fragile components from the rough terrain, dust, and other elements. This frame is perfect for keeping our rover lightweight while still being able to handle the elements and be within the mission's 1.2 meter cube requirements.
Our rover model is designed to include a 5 degree of freedom robot arm with all axes of rotation and all except the lateral axis movement accessible. The arm is intended to simulate ball joint movement, as its attachment to the chassis would allow vertical axis rotation in the same way that a lazy Susan or rotator disc would. At the top of the claw, a brushless motor would be connected to stacked gears, which would use the gears to control the opening and closing motions of the claw.
Same as last year, the rover currently has many different components that we want to use. The program we'll be using for the main movement of the rover will use software called ROS. ROS stands for Robot Operating System and is a set of software libraries and tools needed to help build a robot application. Essentially, this ROS software will give us basic commands and functions within its libraries to help us program. ROS can work with many different programming languages such as C++, Python, and many more.
The rover will be using a Garp brushless motor system for the wheels. Different motors will be used as well for the rover arm and also for the science team's design. Different batteries will be used, including CIM motors. The main batteries used will be the Duracell 12-volt battery, lead acid. LiPo voltage along will be very useful for us since we'll be able to track the voltage of our Duracell 12-volt battery. The ESP32 is a Bluetooth/Wi-Fi device that will allow us to connect with the rover over large distances. This will be very useful for when we have to do one of the rover challenges where the rover must scan QR codes throughout the given area.
This project is split into 4 sub-teams. At the start of the semester, all sub-team leaders met frequently to discuss sub-team needs and coordinate solutions. The sub-team leaders meet twice a week for the project, with Monday meetings serving as general meetings with the whole team, and Friday meetings spent in the workshop to research and experiment with sub-team designs. Club members were able to choose which sub-team they would like to participate in.
The rover's life detection system will collect soil samples using an auger that extends from the underside of the rover into the ground. A thermocouple will also extend from the end of the auger into the ground to measure the temperature of the soil. One of these 4 samples will be weighed again and then heated by a small hot plate to 100 degrees Celsius. The entire experimental bay will be insulated from the rest of the rover's machinery by polyethylene. The remaining 3 samples will be funneled into individual test tubes and secured into place in the tray.
Afterward, each test tube will be filled with deionized water to dissolve the sample into a solution, and one of 3 chemical reagents will then be added to the solution. The tray will be shaken to thoroughly mix all of the test tubes, and each solution will be photographed to examine reactions. Each reagent will present a specific indicator if it reacts with a certain organic marker with the soil-water mixture.
Thank you for listening to our system acceptance review video, and NCSU SEDS cannot wait to further contribute to the URC field.